Okay, so today we are going deep on Google DeepMind's Gemma 3.
Right.
It's the latest in their Gemma series of open models.
Yeah.
And what's really interesting is how it kind of like builds on top of and draws from their Gemini models, or the like big flagship models.
Yeah.
And we're talking about models that come in a whole bunch of different sizes, from a pretty nimble 1 billion parameter model,
Right.
all the way up to a 27 billion parameter model.
Yeah, and it's not just bigger, right? There's actually some pretty neat new features, especially if you're someone who likes to kind of get into the nuts and bolts of machine learning.
Yeah.
So for the first time in the Gemma family, we've got vision understanding.
Right.
So they can actually process images now.
That's pretty cool.
And they've also significantly extended the context window.
Okay.
Up to 128,000 tokens in some of the models.
Wow.
And there are also some pretty substantial improvements in multilingual capabilities.
Nice.
So, yeah, lots to dig into.
And for this deep dive, our primary source is going to be the Gemma 3 technical report.
Perfect.
But we really want to unpack it, explain it for someone who's maybe not like a total beginner in machine learning, but has a good foundation, has a good understanding of the principles, and really wants to know, like, okay, how does this stuff actually work?
No.
And why do they make these choices?
Yeah. And, one of the immediate kind of challenges that comes to mind with these ultra long context windows is what does that do to memory requirements?
Right.
Particularly KV cache.
Yeah.
And so it's interesting, they've actually come up with some really neat architectural innovations to specifically address this and try and reduce that footprint.
Okay, so like what are some of the things that they're doing? I see here they've got they call it interleaved local and global attention.
Right.
It sounds like a pretty neat way of kind of managing the model's attention when it's dealing with so much information.
Yeah, it's pretty clever.
So we're definitely gonna have to unpack that a little bit.
For sure.
And then it's also worth noting that it's not just about these headline features, but the report really emphasizes that there are some tangible performance gains over Gemma 2.
Yeah, absolutely.
And what I found quite amazing was that some of the smaller Gemma 3 models are now performing on par with the larger Gemma 2 models after they kind of go through this refined post-training process.
Yeah.
So it seems like the way they're being taught after that initial training is becoming almost as crucial as the sheer size of the model.
Yeah, for sure.
Which is a pretty big deal, I think.
Yeah, it's a big shift because it means you can get really high performance with more resource efficient models.
Yeah, exactly.
And that's really important.
So let's actually start digging into the nuts and bolts.
Right.
Starting with the overall architecture.
Okay.
They say that, at its heart, it's still a decoder-only transformer architecture.
Right.
So that's going to be familiar if you've worked with previous Gemma models or, other similar language models.
Yeah, so that core building block's still there.
Right.
But there are a couple of key architectural differences that I think are worth exploring.
Okay, like what?
So one of them is that they're using grouped query attention.
Okay.
Or GQA.
GQA.
Yeah, and you can kind of think of that as just a more streamlined way for the model to attend to different parts of the input.
Okay.
Which is particularly useful for speeding up inference.
Right.
Another change is they've transitioned to using QK norm instead of soft capping.
Right.
Which they were using in Gemma 2.
So this is it's all about how they kind of stabilize and optimize the training of these really large models.
Yeah, exactly.
It's kind of a subtle difference, but I feel like those normalization techniques can sometimes have a really big impact.
It really can, yeah.
On how well training goes. But I think maybe the biggest architectural change that really jumps out at me, and this is all related to handling these massive context lengths, is the 5.1 interleaving of local sliding window self-attention and global self-attention layers.
Right.
So can we just break that down? What does that actually mean?
Yeah, totally.
Imagine you've got, a really long document that the model's trying to process. Local attention means that for any given word, the model is only really directly considering the words in its immediate vicinity.
Right.
So in this case, within a 1024 token window.
Exactly.
So it's the model's focusing on a little snippet of the text at any given moment.
Exactly.
Okay.
And then global attention allows the model to look at all of the words in the entire context window, no matter how far apart they are.
Okay.
And so what they're doing in Gemma 3 is they're alternating between these.
Right.
They have 5 local attention layers for every 1 global attention layer.
Okay.
And the whole idea there is efficiency, right?
Right.
Local attention is much, much less computationally expensive.
Right.
But global attention is really important for understanding long-range relationships
Right.
and the overall context of the input.
Okay.
So by using more of these local layers, they can kind of significantly reduce the computational cost
Yes.
of working with these 128K token sequences.
Gotcha.
So it's like, the global layers are responsible for understanding the big picture.
Right.
And the local layers are kind of handling the more immediate granular context.
Gotcha. So the global ones are kind of like setting the stage.
Exactly.
And then the local ones are like, okay, let's really pay attention to this little bit right here.
Exactly. Yeah.
Gotcha.
And this is really key to how they're managing that KV cache memory challenge that we talked about.
Right.
Because by limiting the scope of the more memory intensive global attention,
Right.
they can keep that memory footprint manageable, even with these really long context lengths.
Yeah.
So a really neat design.
That is really clever. And then, of course, there's also just the sheer increase in context length itself.
Yeah.
Right. They're now supporting up to 128,000 tokens,
Huge.
which is, that's a big jump for most of the models. And even the 1 billion parameter models offering a 32,000 dodo token window.
Right.
So, think about what you could do with that, processing entire books or massive code bases.
Absolutely. Yeah. That alone is a game changer.
Yeah.
And to support these longer contexts effectively, they've also made some adjustments to ROPE,
Okay.
the rotary positional embeddings.
Right.
Which are basically how the model understands the order of words in a sequence.
Right.
And so on the global self-attention layers, they've actually increased the base frequency from 10K to 1 million.
Oh, wow. Okay. So what's the thinking behind that?
Well, you can think of it like this. With a much longer document, you need more fine-grained addresses for each word.
Right.
Right. So the model knows where it is relative to all the other words.
Yeah.
So by increasing the frequency, it allows for those more precise location markers within that vast context.
Okay.
However, they've kept the base frequency for the local layers at the original 10K.
Okay.
Likely because within that smaller window of 1024 tokens, the relative positions are already well captured at that lower frequency.
Gotcha. So it's like they're adjusting the resolution of their positional awareness based on kind of the scope of attention. Okay,
Yeah.
that's really neat.
Yeah.
And then they also talk about using positional interpolation
Right.
to extend the reach of global attention. So how does that work?
So positional interpolation is basically a way of taking a model that was trained on shorter sequences
Okay.
and adapting it to handle much longer sequences.
Okay.
So essentially, it scales the positional embeddings that it's already learned.
Right.
So it can kind of extrapolate its understanding of word order to these new extended contexts without needing to be retrained on those longer sequences.
So it's like stretching its knowledge of positional information.
Yeah, exactly.
Okay, that's really clever.
Yeah.
Okay, so let's shift gears a little bit and talk about one of the really cool new features, which is vision understanding.
All right. Yeah, this is a big one.
This is huge.
This is a big step forward for the Gemma family.
Yeah.
So they've actually integrated a 400 million parameter SIGLIP vision encoder
Okay.
into the 4B, 12B, and 27B models.
Gotcha.
And SIGLIP itself is a vision transformer model that's been trained using this contrastive learning approach,
Yeah.
similar to CLIP,
Right.
which essentially teaches it to understand the relationship between images and text descriptions.
Okay.
Right, so you can kind of think of it as it's taking that image as input and transforming it into something that the language model can understand.
Right. So those soft tokens that we were talking about earlier.
Exactly. So it takes in square images that are resized to 896 by 896 pixels
Okay.
and outputs a sequence of these soft tokens that represent the visual information.
Right.
And interestingly, this vision encoder is actually shared across all three of those models, the 4B, 12B, and 27B.
Okay.
And it stays frozen during the language model training,
Okay.
which is actually a pretty significant optimization.
Right. Because I imagine that saves a lot of compute.
This saves a lot of compute, yeah, because you can pre-compute those features.
Yeah, exactly.
Yeah.
So that makes a lot of sense.
Mm-hmm.
But what about like real world images? Because, not every image is perfectly square.
Right.
And some images are, really, really high resolution.
Yeah, good point.
So how do they handle that?
So that's where their pan and scan or PNS method comes in.
Okay.
And this is a really clever inference time technique that they've come up with to specifically address these situations.
Okay.
And the way it works is they divide the input image into smaller, non-overlapping tiles of equal size.
Okay.
And then they resize each of those tiles to that standard 896 by 896 resolution.
Gotcha.
And then feed each one into the vision encoder.
So it's like they're taking, zoomed in snapshots of the image and processing each one kind of individually, and then I guess somehow stitching it all back together.
Yeah, the model then processes each of these crops.
Yeah.
And yeah, you can think of it as kind of stitching it back together.
Okay.
And this is really useful for images with weird aspect ratios or very detailed high-resolution images where you might lose some of those fine-grained details if you just try to encode the entire image at a fixed resolution.
Yeah, totally.
And it's important to note that this PNS is an inference-only optimization.
Okay.
So it's applied when you're actually using the model, not when you're training it.
Gotcha.
And you can also turn it off if you need faster inference.
Okay.
Yeah.
Okay, so that's a really good overview of all the architectural innovations. Now let's talk about how they actually go about training these beasts.
Right.
Starting with the pre-training phase. And I see here they say it's a similar recipe to Gemma 2, but with the addition of knowledge distillation. So can you just unpack that a little bit?
Yeah, so the overall pre-training strategy shares some similarities with Gemma 2.
Okay.
But they've incorporated knowledge distillation, which is basically where a smaller student model learns from a larger, more capable teacher model.
Right.
And they've also slightly increased the amount of data that they're using for training.
Okay.
Compared to Gemma 2.
Like how much are we talking?
So, for example, the 27 billion parameter Gemma 3 model is trained on a whopping 14 trillion tokens.
14 trillion. That is huge.
It's a lot of data.
Okay, so that includes the image and text data, right?
Yeah, exactly.
Okay.
And they've also increased the proportion of multilingual data.
Okay.
To really improve those multilingual capabilities.
Cool.
And they're using a mix of both monolingual and parallel data. And they've actually adopted a strategy that's inspired by a paper by Chung et al. From 2023 to deal with this problem of language representation imbalance,
right?
Which you often see in these large multilingual data sets.
Totally. Yeah, so it's like, making sure that the less widely spoken languages are still being effectively learned.
Exactly.
Okay, that makes a lot of sense.
Yeah.
And then they also note that they're using the same tokenizer as Gemini 2.0.
Right.
So can you just remind us, what are some of the key characteristics of that tokenizer?
Yeah, so the Gemini 2.0 tokenizer is based on sentence piece.
Okay.
And it has a vocabulary of 262,000 tokens.
Okay.
And some of the key features are that it splits digits into individual tokens.
Right.
It preserves white space characters.
Okay.
And it uses byte level encodings.
Gotcha.
And this design is actually really good for providing a more balanced representation across different languages.
Okay.
Compared to some of the earlier tokenizers that might have been a bit biased towards English.
Yeah.
So this is really important for building truly multilingual models.
Right, totally. And then, of course, there's the really important step of data filtering during pre-training.
Oh, yeah, absolutely.
So, how do they actually go about ensuring the quality and safety of such a massive data set?
So they use a whole bunch of different filtering techniques.
Okay.
To try and reduce the presence of things like unwanted content, harmful content, personal information, sensitive information.
Yeah.
They also do a lot of work to decontaminate their evaluation data sets.
Okay.
So that the models don't inadvertently memorize the evaluation data.
Right.
Which can lead to artificially inflated performance scores.
Gotcha.
And they also use a technique called quality reweighing.
Okay.
That was inspired by a paper by Sagdiva et al. From 2024, which basically tries to downweight the impact of lower quality data examples on the training process.
Gotcha.
Yeah.
And then we also can't forget about knowledge distillation. So how does that actually play out in the pre-training of Gemma 3?
So what they do is for each token, they actually sample 256 of the raw prediction scores.
Okay.
Also known as logits. From the larger teacher model.
Okay.
And they weight these samples according to the teacher's predicted probabilities for each token.
Right.
And then the student model actually learns to predict a probability distribution over those sampled logits that closely matches the teacher's distribution.
Okay.
And they use a cross-entropy loss function for that.
Gotcha.
And for the logits that weren't sampled, they effectively set the teacher's target probability to 0.
Oh, yeah.
and renormalize the probabilities of the sampled launches.
Gotcha.
Yeah,
So it's like a really, really efficient way of kind of transferring the knowledge from the bigger model to the smaller model.
exactly. It is.
Okay, that's really cool.
Yeah.
So let's talk about, they're doing all this training, they've got these big models, but how do they make these actually usable in the real world? And one of the things they talk about is quantization-aware training. So can you tell us a little bit about that?
Yeah. So in addition to the regular, floating point versions of the models, they actually provide quantized versions
Okay.
in several different formats. NT4 per channel, NT4 per block, and switched FP8.
Gotcha.
And these quantized models are really useful because they have a much smaller memory footprint.
Right.
And often can run inference much faster.
Yeah, which is really important if you're trying to deploy these things on, hardware with limited resources.
Absolutely.
Yeah. And these quantized versions aren't just obtained through like a simple post-training quantization process.
Right.
They actually use quantization-aware training, right?
Exactly, yeah.
Can you tell us a bit about how that works?
So quantization-aware training, or QAT, involves fine-tuning the model for a small number of steps,
Okay.
typically around 5,000,
Okay.
while explicitly making the training process aware of those quantization constraints.
Right.
So during fine-tuning, they use the probability distributions that were predicted by the original non-quantized model as targets,
Okay.
and they also adapt the data distribution a little bit
Okay.
to better match what they see in both pre-training and post-training.
Okay.
And this helps the model kind of maintain a high level of performance
Yeah.
even after being quantized.
Yeah. So it's like they're sort of baking in the awareness of those constraints from the very beginning.
Exactly.
So it's not as jarring when they actually go through that quantization process.
Exactly.
Okay, that's really smart.
Yeah.
And then the report also includes a really helpful table showing the memory usage of both the original and the quantized models,
Right.
both with and without the KV cache. And this is for a 32K context length.
Right.
And it's pretty amazing to see just how much memory savings they're able to achieve
It really is.
through quantization.
Yeah.
Okay, so let's just briefly touch on the massive computational infrastructure that's required to train these things.
Yeah, it's pretty intense.
Yeah, it's not your average laptop.
No.
So they were trained using Google's tensor processing units, TPUs,
No.
specifically the TPU v4, TPU v5e, and TPU v5p. And they've kind of used different configurations of these TPUs depending on the model size.
Right.
And they're really trying to optimize for minimal step time.
Exactly.
And of course, they also pre-computed the vision encoder embeddings, which we talked about earlier, to kind of save computational costs during the language model training.
Yes, smart move.
And then they also use some other interesting techniques like 0-3 for sharding the optimizer state, which is essentially, a way of distributing that memory burden across multiple devices.
Yeah.
And then they use their pathways infrastructure for communicating and synchronizing across multiple TPU pods. So it's really a very sophisticated setup.
It is.
And it's all being managed using this single controller programming paradigm of jacks and pathways. And then, of course, they're using the GSPMD partitioner and the mega-scale XLA compiler. So it's like the cutting edge of machine learning training infrastructure.
Absolutely.
Okay, so we've talked about the architecture, we've talked about the pre-training. Let's talk about instruction tuning.
Okay.
Because, this is what takes those pre-trained models and turns them into something that's actually useful and can follow instructions and be more conversational.
Exactly.
And they're saying they've got an improved approach compared to previous Gemma versions.
Yeah, they've really refined their post-training strategy.
Okay, so like what's new?
So now it involves knowledge distillation from a very large, very capable, instruction-tuned teacher model.
Okay.
And then they do a reinforcement learning fine-tuning phase.
Okay.
And this RL fine-tuning builds on their previous work with techniques like bond, warm, and warp.
Right.
But they've made some advancements and improvements there.
Okay.
Yeah.
And so, like, what are the main things that they're trying to achieve with this reinforcement learning fine-tuning?
So they're really trying to enhance a whole bunch of different capabilities.
Okay, like what?
So things like overall helpfulness,
Yeah.
performance on more complex tasks like math and coding,
Right.
reasoning abilities, the ability to accurately follow instructions, and multilingual proficiency.
Okay, so really hitting all the key areas.
Exactly.
So, right.
And of course, they're also working to minimize the generation of harmful content.
Right.
And to do this, they use these sophisticated reward functions
Okay.
that are learned from human feedback data.
Okay.
They also incorporate feedback from actually running the code
Right.
that the model generates.
Yeah, to make sure it actually works.
Exactly.
Okay.
And they even use ground truth rewards for evaluating solutions to math problems.
Wow. Okay, so they're really putting it through its paces.
They really are, yeah.
And they also talk about the fact that they're very careful about filtering the data that they use for this post-training phase.
Oh, absolutely.
So can you tell us a little bit about like what kind of data they prioritize?
Yeah, so they're very selective about the data they include.
Okay.
They rigorously filter out things like personal information,
Yeah.
any outputs from the model that are unsafe or toxic,
Right.
instances where the model incorrectly identifies itself,
Okay.
and any duplicates within the data set.
Gotcha.
And on the flip side, they actually specifically include data that encourages things like better in-context attribution,
Okay.
the use of cautious or hedging language,
Right.
and clear refusals to answer harmful or inappropriate queries.
Okay.
So it's all about trying to, minimize hallucinations and improve the accuracy.
Yeah. Yeah. Really trying to make it as reliable as possible.
Exactly.
And then it looks like they've also kind of standardized how they handle the end of a generated sequence.
Yeah, so both the pre-trained and instruction-tuned models use a beginning of sequence, or BOS, token,
Right.
which you need to add during tokenization.
Okay.
But the key difference is the token that signals the end of the generated output.
Okay.
So pre-trained models use an end of sequence, or EOS token.
Right.
Whereas instruction-tuned models use an end of turn or end off turn token.
Okay.
So there's a subtle difference, but it's important to be aware of when you're working with these models.
Yeah, definitely.
Yeah.
Okay. So after all of this, how well do they actually perform?
All right, let's get to the results.
Yeah, let's see how they did.
So they evaluate Gemma 3 on both automated benchmarks
Okay.
and human evaluations.
Okay.
And they actually participated in the LMSYS chatbot arena with Gemma 3.
Oh, cool.
Yeah.
And so like what were the results there?
So the 27B instruction-tuned model actually achieved a really high ELO score,
Okay.
which put it among the top 10 models in the arena
Wow.
at the time. And it was notably higher than its predecessor, Gemma 227B IT.
Okay.
But it's worth noting that these ELO scores don't yet account for visual abilities.
Right. Right. Which is, a big part of what Gemma 3 can do.
Exactly.
Okay.
Yeah.
So what about like the more traditional benchmarks?
Right. So they also evaluated on a bunch of standard benchmarks.
Okay.
And they compare against previous Gemma versions and Gemini 1.5.
Okay.
And these benchmarks look at things like language understanding, code generation, reasoning, mathematical problem solving.
Okay.
And across the board, the data shows general improvements with Gemma 3.
Okay, so they're definitely making progress.
Yeah, for sure.
But they also kind of caution against making direct comparisons with other models just based on these numbers.
Yeah, because the evaluation settings can vary.
Right, between different research groups.
Exactly.
So they recommend checking out community-maintained leaderboards.
Yeah, for a more holistic comparison.
Okay, yeah, that makes sense. So let's talk about some of the ablation studies that they did.
Right.
Because these are always really fascinating, I think, to see how like specific choices impact performance.
Yeah, they could be really insightful.
Yeah.
So one of the key areas they looked at was the impact of those local and global attention layers.
Right. So they were playing around with the ratio.
Yeah, they experimented with different ratios of local to global attention.
Okay.
And it's interesting, they found that it had minimal impact on perplexity,
Oh, wow.
even when they significantly altered the ratio.
Okay.
So, for example, they went from Gemma 2's 1.1 ratio to a 7.1 local to global ratio.
And it didn't really change things.
And it didn't really affect the perplexity much at all.
Okay.
So they ended up settling on a 5.1 ratio for Gemma 3.
Okay.
But this suggests that the model's pretty robust
Yeah.
to different attention allocations.
Yeah, that's kind of surprising, honestly.
It is a bit.
Yeah, because you would think that would have a bigger impact.
Yeah, you would expect it to, but it seems like it's pretty flexible.
Okay, so what about the size of the sliding window for those local attention layers?
Right, so they found that they could actually reduce the size of the sliding window quite a bit
Right.
without really hurting the performance.
So it doesn't need to see that much local context.
Yeah, it doesn't need a super wide window
Okay.
to capture those dependencies.
Gotcha.
Yeah.
And then this design choice with the 5.1 ratio of local to global and the 1024 token sliding window really had a big impact on the KV cache memory, right?
Yeah, huge impact.
Especially when they were dealing with those long sequences.
Yeah, so compared to using global attention only or even Gemma 2's configuration,
Right.
this new approach in Gemma 3 significantly reduces the memory overhead,
Okay.
especially as you get to those longer input sequences.
And they actually quantify how much memory savings they get,
They do, yeah.
which is, I mean, it's pretty substantial.
Yeah, pretty impressive.
Okay, so another interesting thing they looked at was how they enabled that long context capability. So they actually pre-trained on sequences up to 32,000 tokens, and then extended that to 128,000 tokens using rope E rescaling.
Exactly.
So they weren't training on those super long sequences from the start.
Right, it's kind of a two-stage process.
Okay.
Yeah.
And they found that a scaling factor of 8 worked well for that rope E rescaling.
Yeah, and they also increased the base frequency of the rope E embeddings for the global attention layers to 1 million.
Okay.
And they found that the models generalized pretty well to that 128K context length,
Okay.
but performance started to drop off if they tried to go much beyond that.
Okay, so there are still limits.